From measurements of initial rates, I can determine the rate law expression for a reaction. Now, the rate law expression has the general form, rate equals K times the concentration of reactant A raised to some power X times the concentration of reactant B raised to some power Y, and so forth. K is called the specific rate constant for the reaction, and K will change with temperature. The value of X is said to be the order of reaction with respect to A. Y is the order with respect to B. Now, the overall order is X plus Y. So to determine the rate law expression, we're going to look at a table of data. And we're going to compare different trials to determine what the order of the reaction is. So I know that, here's my general form. Rate equals K times the reactant A2 raised to some power X times the reactant B raised to some power Y. I'm trying to determine what X and Y are. And X and Y can be 0, 1, 2, or 3. Those are my possibilities. So in order to determine X and Y, I'm going to compare trials. I will first compare trial 1 and 2. And the reason I'm comparing trial 1 and 2 is you'll notice that A2 is held constant. And since A2 is held constant, I can determine the order with respect to B. B doubles between trials 1 and 2. I'm going to look at the rate. The rate stays the same. It's 4 times 10 to the negative 4th in both cases. So since B doubles and the rate stays the same, the order with respect to B is 0. The reaction rate has nothing to do with the concentration of B. It's 0 order with B. So I can essentially mark that off because B has no effect on the rate of reaction. So now let's look at a couple different trials. Let's look at trials 1 and 3 this time. In between trials 1 and 3, notice what happens to the concentration of A2. A2 doubles. Compare the rate. The rate goes from 4 times 10 to the negative 4th up to 8 times 10 to the negative 4th. So the rate also doubles. If the concentration and the rate do exactly the same thing, it is said to be first order. So the value for X is 1. So here's my rate law. Rate is equal to K times the concentration of A2 raised to the first power. That is my rate law based on the data that I'm given. So here's an explanation that I just kind of went through. There's also a mathematical way, which I will show you in class if you prefer to do the mathematical way. So now we know our rate law. From our rate law, we can determine the specific rate constant K by substituting in data. So my rate law is K times the concentration of A2 raised to the first. If I want to determine what K is, I can substitute any set of data. So let's just substitute in the data for trial 1. The rate on trial 1 is 4 times 10 to the negative 4th, and rate is molarity per second. We want to solve for K. The concentration of A2 in trial 1 is 1 times 10 to the negative 2 molar, and that's raised to the first. Now it's important that we get the right units for K as well. So K is simply equal to 4 times 10 to the negative 4th molarity per second dividing by 1 times 10 to the negative 2 molar. And so the number for the constant is 4 times 10 to the negative 2. And then the units, molarities, cancel out. So the units in this case for K are 1 over S. That's not always the units for K, just in this particular reaction. So pay attention to the units because those are important. And K will not change as long as the temperature stays the same throughout this reaction. Okay, temperature. Temperature affects reaction rate. The average kinetic energy of a collection of molecules is proportional to the absolute temperature, that is the Kelvin temperature. At a given temperature T1, a definite fraction of collisions have sufficient energy to react to form products, but at a higher temperature, a greater percentage of the collisions possess the necessary activation energy. So the reaction will proceed at a faster rate. So let's look at a graph of fraction of collisions versus kinetic energy at two different temperatures. At T1, which is the lower temperature, the average kinetic energy, the peak of the curve, is somewhere about right here. So there's your average for T1. But even at T1, some molecules have kinetic energy way over here, and some molecules have kinetic energy way over here. At T2, the average kinetic energy is right here at the peak. So the average kinetic energy is greater for T2, and that makes sense because T2 is a greater temperature. But even at T2, some molecules have really low kinetic energy, some have really high. At T2, you'll notice that more molecules have the necessary activation energy. This activation energy is just arbitrarily put right here. But at T2, higher temperature, more molecules have enough kinetic energy for the reaction to proceed. That necessary energy barrier will be overcome. In 1889, Svante Arrhenius showed the dependence of the rate constant K on temperature. Now here's a lot of derivations for you. And I'm going to leave these here and I'll let you kind of look through the derivations, but I want to get to the important part. So here's a derivation from the Arrhenius equation. And we can derive it using a hypothetical chemical reaction. But again, there's lots of symbols here, and I will show you the important things. So the Arrhenius equation is right here under number 6. It shows the dependence of the rate constant K on temperature, the absolute temperature, the Kelvin temperature. But we're going to use a different form of the Arrhenius equation. So here is the form that we're going to use for the Arrhenius equation, and it looks like this. Natural log of K1 over K2 is equal to the activation energy divided by R, which is that gas constant, 1 over T2 minus 1 over T1. So this is a different form of the Arrhenius equation, and I will show you how we use this form of the Arrhenius equation in class when we go through some examples. But again, the Arrhenius equation shows the dependence of the rate constant K on temperature. Catalysts are the fourth thing that affect reaction rates. Catalysts can be added to reacting systems either to increase or in rare cases to decrease the rate of reaction, but most of the time we want to increase the rate of reaction, speed them up. Catalysts allow reactions to occur via alternate pathways, and these affect activation energies. So in most catalyzed reactions, the activation energy gets lowered. So here's a couple energy diagrams for an uncatalyzed reaction and then a catalyzed reaction. You'll notice that nothing changes except this activation energy right here. This is without a catalyst on the left. Pretty large activation energy. On the right, what happened to the activation energy is it got decreased because we added the catalyst. It allowed the reaction to occur via a different pathway. Nothing else changed in this reaction. Delta E is the same value. The only thing that was affected was the activation energy. So it makes it quicker because there's less of an energy barrier when you add a catalyst. So the minimum kinetic energy for a catalyzed reaction is going to be less. And the reason this value here is less is because the activation energy got lowered when you added a catalyst. A catalyst can enter a reaction, but it does not appear in the balanced chemical equation. And there are two types of catalysts, homogeneous and heterogeneous catalysts. Homogeneous catalysts exist in the same phase. So for example, hydrogen peroxide will decompose into water and oxygen, but it's a slow process. If I want to speed this up, I add a catalyst. Now catalysts appear above the arrow because they may enter the reaction, but they're not a reactant or a product. They get formed later. This is the actual two-step mechanism by which this reaction happens. So you'll see Br2 enters the reaction, but it's formed later. So Br2 essentially cancels out, and since it was used to start the reaction, it's a catalyst. You'll also notice in this mechanism that the Br minus cancels out and H plus cancels out. Those are known as reaction intermediates. But Br2 is a homogeneous catalyst in this case because H2O2 is a liquid and Br2 is also a liquid, so they're in the same phase. So you can have homogeneous catalysts. You can also have heterogeneous catalysts. Heterogeneous catalysts exist in different phases in the reactants. Catalytic converters in today's automobiles contain two types of heterogeneous catalysts, platinum and nickel oxide, and they form three simultaneous tasks. They will get rid of unburnt hydrocarbons like C8H18. They will reduce or oxidize carbon monoxide, and they will reduce nitrous oxide. So these catalysts, the platinum and nickel oxide, are heterogeneous because they are solids and the reactants are gases in these cases.